For number 37, we're asked to find x dot of t and then sketch the trajectory for this particular initial value problem in our phase plane. We want to use arrows showing our motion, etc. So the problem that we're given, I'm going to scroll over, is exactly the same problem. I did it in the last video here for number 28. So the initial value problem here at the top. That's what we're given. And in the last problem, we did all the work to use this to solve it to end up with an expression for x. We actually ended up with two. So we either had sine of 4t, or we can do it with the cosine, etc. But I'm just going to use the sine of 4t for our expression. So if I can write down, so the initial value problem was that the second derivative of x with respect to time plus 16 x equals 0, and we had some initial conditions here. As I just showed you, we had a solution that said x as a function of time ends up being sine of 4t. Now, if I want to sketch this in my phase plane, I would also need x, well, the first derivative of x with respect to time, or x dot. So in this case, let's take that derivative by the chain rule. We'll have 4 cosine of 4t. So this is what we want to sketch in our phase plane. So let me put up here a little set of axes. So for the phase plane, our horizontal axis is just going to be x, and our vertical axis will be sort of x dot. And you may recall in class I mentioned if you want to, you could think about x dot as your y. And this really just turns into doing a phase portrait for that system of equations. X equals, well, I guess we should write it this way. Your system of equations would be, if we were trying to convert it to that dx dt is equal to y, right? And then dy dt, since that would be the second derivative, that's equal to x double dot, which in this case you can show would be equal to negative 16x. So that's one way you could do it. That's one way you could set up this problem in the beginning. Now, we don't have to do that because we've already done a good amount of work and we've solved it explicitly. But this setup, I'm just putting it here to recognize you could do this even if you don't have the explicit solution, right? Even if we didn't have these two things right here, we could still do this problem. And that's just a nice thing to know. So that's just sort of a little thought to sort of tuck away, right? But since we do have these particular solutions here, we could just, if we chose, pick points, plug it in. So, for instance, when so here I'm going to make a little table if you want to plot your particular solution. So we'll do maybe x. I like to call it y. You could also call it x dot if you chose. So pick a value. So say at time 0, right? X is 0 and y is 4. At time, and pick some other convenient values. So say we did pi over 8. When that happens, sticking pi over 8 into this equation gives you pi halves. So at that point, at pi halves, sine of pi halves is positive 1. And cosine of pi halves is 0. Then, pick a next convenient value, maybe pi fourths. At pi fourths, suddenly sine of pi is 0 again. Cosine of pi is negative 1, etc. So we see this, we get a few points. Maybe we'll pick one more here. Let's just do could do 3 pi-8 if we wanted. If I stick 3 pi-8 in there, that gives me 3 pi halves, which gives me minus -1, and y is 0. So these gives me some points. So at time being 0, we see that we're at x0, y equals 4. So we're up here. As we progress, we're a little bit closer. So this would have been height. 1, 2, 3, 4, and just distance 1. And then go down 1, 2, 3, 4. Over here. So as time goes on, our phase portrait ends up giving us some sort of ellipse. That's kind of a terrible ellipse, but you see what I'm going for. So we get this ellipse, and it goes around in this way. So it's kind of nice. So that can actually, I can use that information to say, well, the arrows then for my phase portrait would go around like so. If I wanted to double check that, I could do it in one of two ways. I could do the same problem with this work here and say, we'll pick a value in, say, this first quadrant. So let's say 1, 1. When that happens, this is positive. So that tells me my x's are positive. The change of x is positive. So it's going to the right. So these are right-ish, heading to the right. But then this value is negative. So it's going down. So that's why these are going to the right and down. If I pick a value down here, say 1, -1, then we have this value is now negative. So we're going to the left. And this value is still negative, so we're still going down. If I pick a value in this quadrant over here, so I guess we'd actually do for first, fourth, we're now in the third. Say -1, -1. Then this is negative, so we're going to the left, but this is now positive, so we're going up. So you could use these to give a general sense, a little thought experiment. But you can also recognize, if I did things with like my null clients in this particular problem are just my axes, and so each quadrant will have its more or less unique sense of the motion. Up to the right, up to the left, down to the right, or down to the left. The other way that I could double check that if I were interested in it is going to a graph. Let me pull up a website. So here we see this website that I like to use a good amount, and we have your system plugged in. dx/dt is equal to y, dy dt is -16x. I would, before I graph things, often change this to a better rule, allow switching, maybe even make h a little bit smaller, and then I can, if I chose, plug in my initial point. We had x was 0 and x prime was 4, so I can plug that in. And here we go. We have our solution. We see that we again have that general sense, and it looks as if all solutions are going to be going around in circles like that, which is expected since this is modeling an undamped spring.